This is equation number 5.37. From equation 5.35, it is obvious. At the center of the sphere, small r is equal to 0. Therefore, A is equal to 0. This is equation number 5.38. At the surface of the sphere, small r is equal to capital R. Then, from 5.37, we have electric field at the surface of sphere of charge. That is, A is equal to capital R rho upon 3 epsilon naught is equal to maximum. This is equation number 5.39. All the above results 5.31, 5.36, 5.38, 5.39 are depicted in figure 5.12, which represents the variation of electric field E vector with distance r from the center of a uniformly charged conducting solid sphere. Here we have a figure 5.12, which represents the variation of electric field due to uniformly charged sphere. We have distance from the center r along x-axis and electric field along y-axis. From point O, the electric field is directly proportional to distance r, but the electric field is inversely proportional to the square of the distance. So now we are discussing field at a point due to an infinite flat sheet of charge. Let P be a point at a distance r from a thin non-conducting infinite sheet of charge, where electric field due to the sheet of is to be calculated. Let sigma be the surface charge density of the charge or charge per unit surface area, and the charge on the sheet be positive. From symmetry, the magnitude of electric intensity on either side of the sheet at all points equidistant from the sheet is same, and it acts perpendicular to the plane of the sheet directed outwards. Consider a cylinder of cross-sectional area ds, length 2r, piercing through the sheet, with axis of the cylinder perpendicular to the plane of the sheet, and one of the plane surfaces enclosing the point P where the intensity is to be measured. Q is a point on the opposite side of the sheet on the plane surface of the cylinder. At P, the direction of electric intensity E vector and unit vector n cap normal to area ds is same. This is also true for the point Q on the opposite plane surface of the cylinder. Therefore, contribution of electric flux due to both the plane surfaces of the cylinder is equal to 2 E vector dot n cap dot ds is equal to 2 E dot ds, because E vector is parallel to n cap. The curved surface will not contribute towards the electric flux through the cylinder, as electric intensity E vector and n cap at all points of the curved surface are directed at right angle to each other. Thus, total electric flux through the whole of the surface of the cylinder is 2E dot ds. The cylinder encloses a surface Q is equal to sigma dot ds. Therefore, from Gauss law, 2E dot ds is equal to Q upon epsilon naught is equal to sigma dot ds upon epsilon naught. or E is equal to sigma upon 2 epsilon naught. This is equation number 5.40. Or in vector notation, E vector is equal to sigma r cap upon 2 epsilon naught. This is equation number 5.41. It may be seen from relations 5.41 the electric field is independent of the distance of the point from the plane. It acts perpendicular to the sheet of charge, and in this case where sigma is greater than 0, it is directed away from the shell. It will be directed towards the sheet when charge on the sheet is negative or sigma is less than 0. Electric field due to infinite plane conductor having charge density sigma. In case of a plane conductor, the charge is present on both the surface of the plane. So it is equivalent to two plane sheets of charge, and the charge enclosed by the Gaussian surface will be Q is equal to sigma of 2 dot ds. Therefore, using Gauss law, E dot ds plus E dot ds is equal to Q upon epsilon naught is equal to sigma into 2 ds upon epsilon naught, or E is equal to sigma upon epsilon naught. Example: the electric field due to infinite charged conductor is also independent of distance. Mechanical force per unit area of a charged conducting sphere. Let us consider 2 points P and P dash lying in vacuum and infinitely close to the surface of charge density. Further, suppose that P lies outside and P dash inside the conductor. As shown, the magnitude of electric field at P is given by E is equal to sigma by epsilon naught according to Coulomb's theorem, and may be thought of as composed of the following two parts. Example: first, electric field E1 at P due to charge on small part of the surface area, say del F, very near to the point P. Second, electric field E2 at P due to charge on rest of the surface of the conductor. As these two fields act in the same direction, so E is equal to E1 plus E2 is equal to sigma by epsilon naught. This is equation number 5.42. Now consider the point P dash lying just inside the conductor. The electric field at P dash also consists of two parts. First, the point field P dash due to the charge on the area element del S is minus E1. This part of the field is reversed in direction because P dash lies on the opposite side of del S. Second, the field at P dash due to rest of the surface is again E2 and remains unaltered in direction. Thus, the total field at P dash is minus E1 plus E2, which is equal to 0 as P dash lies inside the conductor. Example: minus E1 plus E2 is equal to 0, or E1 is equal to E2. Putting this in equation 5.42, we get E1 plus E2 is equal to 2. E1 is equal to 2 E2 is equal to sigma upon epsilon naught, or E1 is equal to E2 is equal to sigma upon 2 pi 2 epsilon naught. That is, a unit positive charge on del S experiences an upward force sigma upon 2 epsilon naught due to the charge present on the rest of the surface. This force acts along the outward drawn normal to the surface del S. Total charge present on the area element del S is equal to sigma dot del S. Therefore, force experienced by the area element del S of the charged surface is equal to F is equal to sigma dot del S into sigma upon 2 epsilon naught is equal to sigma square del S upon 2 epsilon naught. This is the mechanical force experienced by an area element del S of the charged conductor. Hence, the mechanical force per unit area of the charged conductor is Pe is equal to sigma square upon 2 epsilon naught. This is equation number 5.43. But from Coulomb's theorem, A is equal to sigma upon epsilon naught or sigma is equal to epsilon naught E. Therefore, equation 5.43 may be written as Pe is equal to epsilon naught E square upon 2 Newton per meter square. The direction of this force will be along outward normal to the surface. Example, the surface of a charged conductor is thus always under electric pressure. In a medium of dielectric constant, electric relative permittivity K, the equation 5.44 becomes Pe is equal to epsilon naught Ke square upon 2 Newton per meter square. This is equation number 5.45. One of the practical examples of demonstrating the electrical pressure experienced by the surface of a charged conductor is bulging of a soap bubble on charging. Energy stored per unit volume in an electric field. As explained above, the mechanical force per unit area, equation 5.44, experienced by a charged surface put in vacuum is given by Pe is equal to epsilon naught of E square by 2. Mechanical force on the element of area del S is given by F is equal to Pe into del S is equal to epsilon naught dot E square upon 2 into del S. Now, if the area element del S is moved normally through a distance del x against the electrical force F vector, the work done is given by W is equal to epsilon naught E square by 2 del S dot del x. The volume swept through is equal to del S dot del x. Hence, the work done in producing unit volume of the field is epsilon naught E square by 2, which is the energy stored per unit volume of the media. Thus, the energy stored per unit volume of the media is equal to epsilon naught E square upon 2 joule per meter cube. This energy appears in the form of energy of strain in the media. It may be noted that in some cases this strain is very large and the dielectric gets punctured. The electric field at which the dielectric gives way is known as dielectric strength of the media, and it should be avoided for keeping the dielectric intact. If the conductor lies in media of dielectric constant K, then the energy stored per unit volume of the media is equal to E square K epsilon naught upon 2 joule per meter cube. Now we have some examples. Um, Example number 7. The air pressure is the same inside and outside a soap bubble of radius 1 centimeter. Calculate the charge on the soap bubble if the surface tension is 3 into 10 to the power minus 2 Newton per meter. The solution is radius of the soap bubble R is equal to 1 centimeter equal to 0.01 meter. Surface tension T is equal to 3 into 10 to the power minus 2 Newton per meter, as the pressure inside and outside is the same. So mechanical pressure of the charged bubble PE is equal to 4T by R or sigma square upon 2 pi epsilon naught is equal to 4T by R, where sigma is the charged density. If Q be the charge on the surface of soap bubble, then sigma is equal to Q upon 4 pi R square. Therefore, Q upon 4 pi R square whole square into 1 upon 2 epsilon naught is equal to 4T by R, or Q square is equal to 16 pi square into R की power 4 into 2 epsilon naught into 4T upon R is equal to 128 pi square R cube T upon 36 pi into 10 to the power 9. Because epsilon naught is equal to 1 upon 36 pi into 10 to the power 9 coulomb per Newton per meter square is equal to 32 into pi R cube T upon 9 into 10 to the power 9, or Q is equal to 32 pi R cube T upon 9 into 10 to the power 9 की whole power half into 2 pi R T की power half is equal to 4 by 3 R by 10 की power 4 into 1 by 2, which is equal to 4 by 3 into 0.01 upon 10 की power 4 brackets 2 into 22 by 7 into 0.01 into 3 into 10 की power minus 2 upon 10 की power half is equal to 4 by 3 into 10 की power minus 6 bracket started 132 into 10 की power minus 4 upon 70 bracket closed power half is equal to 4 by 3 into 10 की power minus 8 bracket 132 upon 70 की power half is equal to 4 by 3 into 10 की power minus 8 into 1.373 equal to 1.830 into 10 की power minus 8 coulomb. Next example is example number 8. An insulated soap bubble of 10 cm radius is charged with 7 into 10 की power minus 9 coulomb. Find the increase in radius due to the charge, neglecting surface effect, given the atmospheric pressure is equal to 10 की power Newton per meter square. The solution is, if R be the original radius of the bubble, then volume of the bubble V is equal to 4 by 3 pi R square. And if P be the atmospheric pressure, then from Boyle's law, PV is equal to constant is equal to K, or P is equal to K by V is equal to K upon 4 by 3 pi R cube. is equal to 3k upon 4 pi r cube is equal to capital K upon r cube, where k is equal to 3k upon 4 pi. This is equation number 1. Let dr be the increase in radius due to charge q on the bubble and dp be the excess pressure on the bubble due to charge. Then dp is equal to sigma square upon 2 epsilon naught is equal to 1 upon 2 epsilon naught bracket started q upon 4 pi r square bracket closed whole square is equal to q square upon 32 epsilon naught pi square r की power 4. This is equation number 2. From relation 1, dp by dr is equal to minus 3k upon r की power 4 is equal to minus 3p by r, or dp is equal to minus 3p upon r dot dr. This is equation number 3. From 1 and 3, dr is equal to q square upon 96 pi square epsilon naught p r cube. Substituting q is equal to 7 into 10 की power minus 9 coulomb, r is equal to 10 centimeter equal to 0.1 meter. P is equal to 10 की power 5 Newton per meter square, and 1 upon epsilon naught is equal to 36 pi into 10 की power 9 Newton meter square per coulomb square. We get dr is equal to 7 into 10 की power minus 9 का whole square into 36 pi into 10 की power 9 upon 96 pi square into 10 की power 5 into 0.1 cube is equal to 49 into 36 upon 96 into 22 by 7 into 10 की power minus 11, which is equal to 5.84 into 10 की power minus 11 meter. There are some more examples. So this is all about this chapter. So thanks.